Hello everyone, and welcome to this video tutorial in which I want to go through the Electromagnetism assignment for solutions. This assignment is about dynamics in electromagnetism, the relativistic formulation of electromagnetism, and the Lagrangian formulation of electromagnetism. This is for UCD students taking the module PHYC 30070. Okay, so let's get right into it. Let's look at question 1 on assignment 4. So here it is. It's about inductance and energy, and there are several different parts to this question, all on this same theme, but each one is kind of rather different. So let's just look for a start at question 4.1a. So we have a long solenoid of radius a with n turns of wire per unit length, carrying a time-dependent current I of t in the circumferential phi hat direction. So we're supposed to use the quasi-static approximation, so it tells us to find the electric field, the magnitude and direction, at a distance s from the axis, both inside and outside of the solenoid. So here, because we've got a time-dependent current I of t, we're looking at a dynamical problem. However, within the quasi-static approximation, the idea is we use the Biot-Savart law to calculate the magnetic field due to the current, but then we just endow that magnetic field with a time dependence inherited from the time dependence of the current. Now, of course, that's not strictly correct. However, it is a good approximation, as we saw in one of the last lectures of the course. So with that time-dependent magnetic field, we can then calculate the induced electric field using the Flux Rule. So that's the logic of the question. So let's get into it. So every question begins, of course, with a diagram, if for no other reason than just to set our convention about the axes and the units and so on. So here we have the solenoid. It has a radius a, n turns of wire per unit length, and the axis running along the z-hat direction, which I've defined going to the right here. So for a steady, time-independent current, I0, we can use Amperes Law. So when writing answers to these questions, one should also always give this kind of detail. Fully explain your answer. So for a steady time-independent current, let's call it I0, Amperes law tells us that the magnetic field at a position r and as a function of the current I0, when applied to the solenoid, gives us this classic result. We get a strong, uniform magnetic field along the axis of the solenoid, so in the z-hat direction, which depends on the current I0 and on the turns per unit length n. That's when we're inside the solenoid, so when the radial extent s is less than the radius of the solenoid a, and it is equal to 0 when outside of the solenoid. So this is a classic result. I'm not going to derive it again. We've derived it many times in the lectures and also in the previous assignment. So I'll just take it as read that you know how to do that. It's a result that you should certainly know. So that's the situation for a steady or time-independent current, and we get there using Amperes law. In this sense, the solenoid is kind of like the magnetic analogue of a capacitor, where you have a strong, homogeneous or uniform electric field between the plates of the capacitor, but 0 outside. Here we have a strong, uniform magnetic field inside the solenoid and 0 outside. But here we have a dynamical situation because the current is actually time dependent. The current is I of t. Therefore, in principle, you would have to solve the full Maxwell's equations. But we're told in the question that here we can resort to the quasi-static approximation. And the quasi-static approximation in this context can be stated extremely simply. It's that the magnetic field B at a position r and at a time t is approximately equal to the B naught that we've just calculated in the steady or time-independent current case at position r, but instead of evaluated at constant current I naught, we take it to be at the time-varying current I of t. And here I'm really just using this result in here. So this is clearly an approximation, but it turns out it's rather a reasonable one if our time dependence of the current is not very, very quick. So that's the approximation. So let's go ahead now and calculate the electric field that follows from the flux rule. The flux rule tells us that the rate of change of the magnetic flux is equal to minus the EMF. And the EMF is the work done per unit charge in driving that charge around a circuit. And of course, the work done is against the electric force, the electric part of the Lorentz force. And so we can write this simply in terms the integral around a loop of the electric field dot dl. dl is the line element which traces the path of our loop. And this loop, of course, is an Amperian loop of radius s. And it's, of course, coaxial with the solenoid. Because we've picked an Amperian loop, the path that we're integrating around is always parallel to the electric field. And so we can just write this as the circumference of that loop, 2 pi s, times the electric field strength. And of course here I'm implicitly using the fact that the electric field is indeed circumferential and parallel to the Amperian loop at every point along that loop. Good. So what is the flux through the loop? We call that phi, and of course in this case it's time dependent, so let me mention explicitly that it's phi of t, and we actually have two distinct scenarios depending on whether we're inside the solenoid or outside. And I can simply read that off from looking at these two expressions for the magnetic field. The magnetic field is only inside the solenoid, and so we have two different cases. If we're inside the solenoid, we have pi s squared b of t, and if we're outside, we have pi a squared b of t. So the s squared result is something that pertains when s is smaller than the radius of the solenoid s less than a, whereas the a squared result pertains when the radius of the loop is greater than the radius of the solenoid. And we can now just substitute in our results for b of t, which I can do pretty straightforwardly. That's going to give us mu naught n I of t within the quasi-static approximation, pi s squared for s less than a, but it's going to give us mu naught n I of t pi a squared for s greater than a. So there are our two results for the flux. So now I just need to take the time derivative of this and then divide by 2 pi s, and I'll be able to find the electric field strength following from the Flux Rule formula. And that gives us the following result for the strength of the electric field E at a point r and time t. Again, we have to divide it up into two cases, depending on whether the radius we're looking at away from the axis of the solenoid is less than or greater than the radius of the solenoid. And these are our final results for the strength of the electric field, and we see that it is given in terms of the rate of change of the current di by dt in both cases. So if we were given in the question a specific form of I of t, for example, cosine omega t or something like that, then we could actually perform that derivative and just write that in here. We know that the electric field is circumferential, so we can actually restore the vectors here by putting a vector on the top of the electric field and putting in the phi hat direction there as well. Good, so that's not so difficult when we have the logic of the question straight. Part B of question 1 asks us to find the self-inductance per unit length of a long solenoid of radius a with n turns per unit length. So again, we're going to assume that there's no longitudinal current. We're going to assume that because the solenoid is long, as we're told in the question, that we can avoid mention of edge effects and so on. So let's just again write down the classic result for the magnetic field in a solenoid. Again, we have to divide it into cases, depending on whether or not we're inside or outside the solenoid. And what I would like to know is the flux through a single turn of wire. We're talking about the magnetic flux, of course. So let's call this flux through a single turn of wire phi I, and that's going to be, by definition, the magnetic field dotted into the vector area of that loop. And we know that it's constant inside the solenoid, and so that's just going to be pi a squared b, which is pi mu naught n I a squared. And therefore the total flux through, let's say, length L of the solenoid. I have to specify a length L because what I know is the turns per unit length, right? So the total phi is therefore just the sum of those individual turns, so that's going to be an extra factor of n in here, so mu naught n squared pi a squared times the current through a single loop I times the length. So n is the turns per unit length, L is the length. And we know that the flux is related to the current through the self-inductance. This is the defining equation. The phi is equal to L times the current. And using that, we can extract the self-inductance L. Mu naught pi n squared a squared L. And the self-inductance per unit length, therefore, is just to divide this by L, and then that L gets crossed off here, and so the final result for the self-inductance per unit length, as requested in the question, is mu naught pi n squared a squared. Very straightforward. Okay, so part C. A conducting planar circular ring of radius r0, centered at the origin and initially in the xy plane, with z equals 0, rotates with a constant angular velocity, omega equals omega x hat, around the x-axis. So let's draw a little sketch of this before we continue. So here I have defined my coordinate system, my right-handed set, x, y, z, and we're told that the ring lies in the xy plane. So there it is, my ring lying in the xy plane, but we're told that the ring is rotating with a constant angular velocity omega around the x-axis. So the sense of rotation of this ring is in this direction, right? So it's not rotating around its axis, which would be the z hat direction, but rather the ring is kind of rotating around the other axis, the x hat direction. It says that the ring is embedded in an external homogeneous magnetic field, and that thing is pointing in the z direction. So I'm going to write that the B here is parallel to the z-hat direction, as you can see from the diagram. And it's constant in time, constant magnetic field, and it's homogeneous, which means it's uniform in space. Derive the electromotive force, epsilon of t, so something that's time-dependent, induced around the ring. If the ring contains a light bulb of resistance R, what is the electric power, P of t, dissipated by the light bulb? So we want to know that the energy is, of course, converted into heat and light, and we want to understand that through the electric power. The light bulb, of course, here it just means that there's a resistor, essentially, in the circuit. Okay, so first of all, we're asked to find the electromotive force. That's a straightforward one. We use the flux rule. Again, always flag up your answers as much as possible to let me or the examiner or whoever know exactly what you're doing. It also helps to structure your own thoughts. So the EMF, epsilon of t, is given by the flux rule as minus the rate of change of the flux. Should always give a bit of commentary on what you're calculating and how you're calculating it. The flux here is itself defined, the magnetic flux, of course, as the magnetic field flux through some particular vector area, dA. And in this particular case, we're talking about a ring. We want to know the magnetic flux through the wire ring, but the ring is rotating. So what's the implication of that? Well, it means that the vector area here is changing. The dA is something that has a vector associated with it. The vector is the unit vector normal to the surface through which, the sort of cross-sectional surface through which we're calculating the field flux, and that object is changing. So the vector itself is rotating. So what we want to know is the component of the magnetic field through that vector area. We do that through the dot product, and obviously that's going to give us a cosine omega t term. So the important point is that in this problem, our phi is time-dependent phi of t. It's the homogeneous magnetic field B times pi. The ring is of radius r0. And this would be the result if the ring was in the xy plane, and remains so, but of course actually it's rotating, and therefore we pick up the extra term cos omega t. And again, that's just the component of B through the ring, considering this vector area dot product here. So the flux is changing, not because the magnetic field is changing, but because the ring that we're considering is moving. And therefore, we can work out the electromotive force from this expression, which is just B pi r naught squared omega sine omega t by taking the derivative. Very straightforward. Once we've understood the logic, so the hard part of this, of course, was working out this time-dependent flux. But when you see it sort of, when you see the vectors and you see it visually, it's fairly straightforward. Okay, so with that in mind, we want to work out the power. So if the circuit contains resistor, then we know, of course, the power P is equal to V times I, the voltage times the current. Written another way, we can write this as V equals I squared R by Ohm's law, or V squared over R, all equivalent forms. We, of course, want the last form of this because the electromotive force is the work done per unit charge in moving a charge around the circuit. So it's related, of course, to the voltage. So epsilon of t is, of course, V of t when we're considering a circuit such as this one, and therefore the power P of t is simply this thing squared divided by R. It's B naught squared divided by R, omega squared pi squared R naught to the 4, because we're squaring everything, sine squared omega t. So here I'm just writing B naught to emphasize that it's the bare B, if you like, rather than the thing that's changing in time. And so if we were to make a sketch of the power evolved in this through this circuit as a function of time, it has this oscillatory behavior. Excuse the bad sketch, but a sketch notwithstanding is always pretty useful to see. It's something that is always positive because we have sine squared. The period, of course, is controlled by omega, and then we have this maximum value here, which is precisely this constant B naught squared omega squared pi squared, running out of space, R naught to the 4 over R. And this goes down to 0, of course. So because we have something that is rotating, we end up with an AC current and an oscillatory power. Okay, so question 4.1d. This is a bit more complicated. We have a long cylinder of radius r carrying a uniform surface charge density sigma. So we imagine that we have some metal cylinder and it's charged up. The charge per unit area on the surface of the cylinder is sigma. So this cylinder is initially at rest, and then it starts to rotate around its central axis, which I've illustrated here with this omega around the z-hat direction, which I'm taking to be the axis of this cylinder. So it begins at rest, but then it starts to rotate. The cylinder begins to rotate, it says, around its central axis. Its angular velocity increases from 0 to a final value of omega naught over a time delta t. So this is a dynamical situation with a changing omega of t and therefore a changing surface current on the surface of this cylinder. In particular, though, we know that for time t greater than delta t, then omega of t is equal to its final value, omega naught, is constant. And that is then a sort of steady-state static situation that we can consider. Of course, the cylinder is rotating, but all the fields, electric and magnetic fields, are going to be constant. The current is going to be constant. We also know that for t equals 0, omega of t is equal to 0. That's the starting condition, where nothing is moving. There are no electric and magnetic fields, there's no energy in that, there's no energy associated with the sort of rotational motion, the kinetic energy of the cylinder itself. So the question says, with respect to the rotation axis, the moment of inertia per unit length of the cylinder is I upon L. how much energy per unit length, W over L, does it take to spin up the cylinder, meaning to get it going from rest to its final value of omega naught in the time delta t? And then it gives us a hint. It says find the answer by considering the final energy stored in the magnetic field and the final kinetic energy of the cylinder. And of course, that's a static situation. It's steady currents, steady fields, all steady state. So let's consider the final magnetic field of the system. So we're going to consider the magnetic field after everything has reached steady states at t greater than delta t. It's B at a position R at a time t greater than delta t. And it's can be treated basically as a solenoid because we have a surface current that's rotating or flowing, if you like, on the surface of this cylinder. Of course, the physical situation is that it's a charged cylinder that's rotating, but that, of course, gives rise to a surface current. And we, therefore, can just use the result for the solenoid to extract the final magnetic field. When we're looking at a radius within the solenoid, S smaller than the radius of the solenoid, R, we have this result, where the surface current is sigma omega naught. So that's playing the role of the n turns of unit length times the current through a single loop. This is a surface current, sigma omega naught. And when we're looking outside the solenoid, as usual, the magnetic field is equal to 0. So if we have a long solenoid where the length L here is much, much greater than the radius R, we can ignore the edge effects, the so-called fringing fields. And the energy stored in the solenoid's magnetic field is, let's call that W mag for the magnetic energy, is given by the usual formula. We integrate in the volume of the space we're considering of the magnetic field strength squared, B squared, d tau. And of course, because the magnetic field is only finite within the solenoid, that ends up, and it's constant within the solenoid, we can simply do this integral. It's a half mu naught pi sigma squared omega naught squared r to the 4 times L, where L is the length of the solenoid. So this we just integrate over the volume of the cylinder, which is, of course, pi r squared L, and then multiply that by the magnetic field within the solenoid. So if we want to know the work done, or the energy contained in the magnetic field per unit length, then we just divide this by L, and then this L gets cancelled over here. And what I've written here is the energy stored in the magnetic fields. And it's that's the total energy stored in the magnetic field, because there's zero magnetic field outside of the solenoid. So if we're going to consider how much energy we need to put in to get this thing rotating, it's of course not just the kinetic energy, but also the magnetic energy that we're creating, that we're then storing in these magnetic fields. Let's, however, now look at the kinetic energy. Again, we're going to consider the case t greater than delta t, where everything's settled down and is constant. This energy we'll call W ke for kinetic energy, and we know the formula. It's a half I omega squared, which in this case is omega naught squared if t is greater than delta t. And so the kinetic energy per unit length is just a half omega naught squared I upon L. I here, don't forget, is the moment of inertia of the cylinder, okay, not the current. So the total energy of the cylinder when it's spun up is just the sum of these two terms. I'll call that the total energy, W total, per unit length divided by L, and I can just collect up some of these terms. Omega naught over 2, mu naught pi sigma square r to the 4, plus I over L. So that's the final energy stored in the system. So what we're asked in the question is, what is the work done to spin up the cylinder? And initially, there's zero energy in the system because there is no rotational energy associated with a spinning cylinder because it's not spinning initially. And there's no energy stored in the magnetic fields because the magnetic fields are zero initially because nothing is rotating and there's no current essentially flowing around the surface of the cylinder, which means it's not a solenoid, it's just a charged cylinder. So initially, we have basically zero magnetic energy and zero kinetic energy. And finally, we have this expression for the total energy of the system. And energy is conserved. And so the energy it takes to get this thing up to its final spinning angular velocity of omega naught is actually precisely this amount of work. Okay, so that question was all about the dynamics of solenoids and self-inductance. It was about the EMF. It was about the work done at energy in fields and so on and so forth. Let's turn now to question 2 of assignment 4. It's about the potentials and the so-called Poynting vector. So we're given in the preamble to the question these following information. It says a given electrodynamical system has an electric scalar potential V equals to 0, and a magnetic vector potential A is A naught sine kx minus omega t in the y direction, where A naught, k, and omega are constants. Now this question is being a little bit imprecise actually, so this is a good opportunity to correct something. If we have a dynamical system that's changing in time, then the electric and magnetic sides of the theory become sort of intertwined, and so we cannot really speak of an electric scalar potential. So this word here is wrong. We should just talk about a scalar potential. And in the dynamical system, we usually call that scalar potential phi, so let's just correct that. And likewise, we don't have a magnetic vector potential. We just have a vector potential. So we should really be more precise. If it's an electrodynamical system, we just have a scalar potential phi and a vector potential A. That doesn't really change anything in the question, but let's be precise about things. Okay, so part A, calculate the electric field and the magnetic field in this system. So that's not so difficult. We just need to relate the electric and magnetic fields to the potentials, and that looks like this. First of all, we have the magnetic field B at a point r in space and time t is just given by the curl of the vector potential at the same point in space t, r, and at the same time t. That's one of the two equations. The other one is how the electric field at position r and time t is related to the potentials, and that is minus the gradient of the scalar potential at position r and time t. That would be the electrostatic part of it, but then there's also the dynamical part that involves the vector potential. Again, everything is evaluated at position r and at time t. So with the magnetic field, we need to compute this curl. We can do it in the usual way as a determinant we'll do it in Cartesian coordinates. If we're doing it in any other coordinate system, we'd have to look up the representation of this gradient operator in whatever coordinates we want. In Cartesian coordinates, it's just a vector dx, dy, dz, and then the components of A are ax, ay, and az. We know from the question that the vector potential is only something that is finite along the y direction. So in this particular question, ax and az are out straight away, and that makes our life very easy, and then we can just write this curl extremely simply, because the x and y components of the curl will be 0, and the z component that features the ay just involves the x derivative of that. And so we just end up with this expression. Extremely simple. Or put another way, B is k a naught cos of kx minus omega t in the z hat direction. What about the electric field? Well, we are told in the question that the scalar potential is equal to 0, so this first term here doesn't contribute, so now we just have the time derivative of the vector potential, and again, that's pretty straightforward. And we're just going to pick up a factor omega a naught cos kx minus omega t, and of course this continues to be in the y direction. Okay, so that's just very straightforward application of the definitions of the electric and magnetic fields in terms of the potential. No worries there. Part B, calculate the Poynting vector. It's given as a cross product between E and B divided by mu naught. So if I take the cross product of something along the y direction and something along the z direction, then the result is going to be along the x direction. That's because the cross product gives us a vector that's mutually perpendicular to the two vectors, and we have a right-handed set. So E cross B is, of course, along the x direction. And indeed, because it's E cross B rather than B cross E, and because we have a right-handed set, it's in the positive x direction. So this object is very simply a naught squared k omega over mu naught times cos squared of kx minus omega t in the positive x direction. Again, that's pretty straightforward. We see that the energy is being transported along the x direction. So this is kind of the meaning of the Poynting vector is the direction of energy flux. It's the energy flux density, actually. And this, of course, makes eminent good sense because the energy is being transported along the x direction, and this vector potential is describing an electromagnetic wave propagating along the x direction, as you can see in here. So the energy is being transported in the direction of propagation of the wave, as you might expect. We have to work out the time averaged value. This cosine here oscillates between 0 and 1 because it's cosine squared, of course. So we oscillate between 0 and 1. If we take the long time average, the average value of that object is going to be 1/2. And so it's extremely simple to work out the time averaged value denoted by these angle brackets, which is just going to be a naught squared k omega upon 2 mu naught. Although this is an averaged value, it's an averaged value of a vector, so it still has a direction, and it's still pointing in the x hat direction. Okay, so returning to this idea of this being an electromagnetic wave, in part C, we're told to use the condition omega equals ck and use Maxwell's equations to show that this is indeed an electromagnetic wave propagating in the vacuum. So the important word here is that it's propagating in the vacuum. What that means is there's no charges or currents anywhere around. Okay, so also we confirm that this is indeed an electromagnetic wave with omega equals ck because we can plug this condition omega equals ck into our definitions of the electric and magnetic fields, and when we do that, we'll confirm the standard result for an electromagnetic wave, that the magnetic and electric fields are actually slaved to each other in this way, where x hat is, of course, the direction of propagation of the wave. So this is indeed an EM wave travelling at velocity v equals c, the speed of light. Okay, we're asked to confirm Maxwell's equations and show that they refer to the vacuum. Let's compute, therefore, the divergence of the electric field. We know the electric field, so let's calculate the divergence of it. Given that it's only something that exists along the y direction, the divergence just involves d by dy of Ey. And, of course, looking at this expression, we see that this doesn't depend functionally on the parameter or the variable y, and so d by dy of Ey is equal to 0. And that implies, of course, that the charge density is equal to 0, because we know that the divergence of the electric field is related to the charge density according to Maxwell. Let's have a look at the divergence of the magnetic field. By exactly the same kind of logic, we would see, because the magnetic field is something that's directed along the z direction, but that the magnitude of this doesn't depend on z, again, we would conclude that the divergence of B is equal to 0, and again, that is something we expect from Maxwell's equations. The divergence of B should be equal to 0. What about the other two Maxwell's equations? Let's have a look at the curl of the electric field. This is going to be minus omega k a naught sine of kx minus omega t in the z direction. And obviously that's equal to minus the time derivative of the magnetic field, which we can see from here. It's in the z direction. If I take minus the time derivative here, I get precisely this result. Which is, again, exactly what we want. Finally, let's look at the curl of the magnetic field. That's going to be k squared a naught sine of kx minus omega t in the y hat direction. And again, we can relate that to the time derivative of the electric field, because that's also something that points along the y direction. And when we look at the specific constants involved, we see it's 1 upon c squared dE by dt. Both of those things satisfy Maxwell's equations. In the vacuum, so specifically, we have that the current density must be equal to 0 for Maxwell's equations to be satisfied. And so what we see is that the electric and magnetic fields here obey all of Maxwell's equations, provided that ρ is equal to 0 and J is equal to 0, implying that it's a vacuum situation. Question 3 on assignment 4 is about the potentials, the electromagnetic potentials, and gauge transformations of the potentials. Again, let's be specific and refer to the scalar potential as phi rather than v, just to get the convention properly sorted. So I'm just going to go through and change all the v's to phi's. This is this gauge transformation there, and this is also a phi. Okay, so the question says, given an electrodynamical system described by scalar and vector potentials phi and a, and they take a specific form that you'll see there. And they're in terms of a function f of t, and this is some time-dependent scalar function. So this is just, it could be cos omega t or whatever. So in part A, it says derive expressions for the electric and magnetic fields. Okay, this is similar to the previous question, so let's, without further ado, just to get straight into it. The magnetic field is related to the curl of the vector potential, and in this case, we'll factorize out the constants, q2f of t over 4 pi epsilon naught. They're just the constants, and therefore notes that we're taking the curl, that's something that refers to spatial derivatives, so f of t is blind to that, it's just something that depends on time. So in the end, we're just really taking the curl of r hat upon r squared, and that's a classic result that we've come across before, and it's equal to 0. One way of seeing that is to express this object r hat over r squared as the gradient, or minus the gradient, of 1 over r, and then notice that the curl of the gradient is equal to 0. So all of this stuff is just equal to 0. Okay, so that's rather interesting. The magnetic field is actually 0, despite these complicated forms to the scalar and vector potentials. What about the electric field? Well, this better not be 0, because then everything would be 0, and then we wouldn't expect to have any kind of potentials. So that's just a sanity check. The electric field is given by the gradient of the scalar potential minus dA by dt. And again, we'll just factorize out the constants, minus q1 upon 4 pi epsilon naught. We have the gradient of 1 over r from the scalar potential, and then minus q2 over 4 pi epsilon naught, and then we've got to take the time derivative here, and so indeed we get df by dt. I'm converting that into a total derivatives with straight d's there, because f only depends on time, and then that whole thing is multiplied by r hat over r squared. So let's just go ahead and compute those things. In particular, notice that we have the gradient of 1 over r, and we just discussed this. The gradient of 1 over r is r hat over r squared, which is shared in common with the second term. So we can tidy this up a bit, is the punchline. We're going to get 1 over 4 pi epsilon naught into q1 minus q2 df by dt into r hat upon r squared. So what is this electric field? We see that it's something that has the usual 1 over r squared form, and it's radially directed. This is the electric field of a point charge. Also notice the correct prefactor, 1 upon 4 pi epsilon naught. But instead of just having a point charge q, we have an effective point charge, which is q1 minus q2 df by dt. So it's like a point charge where the charge itself is changing as a function of time according to this second piece here. A little bit weird, but that's what we've discovered. Okay, so part B is to use this information to find expressions for the charge density and the current density, and we do that simply via Maxwell's equations. So when using Maxwell's equations, just flag it up in your working to make sure everyone's on the same page. The charge density, rho, evaluated at a position r at time t, is just epsilon naught times the divergence of the electric field, and we've just worked out the electric field, and we know that when we take the divergence of r hat upon r squared, we get a delta function. This again confirms our conclusion that this is actually behaving like a point particle. So this is the delta function in 3D space, which pins us to the origin. So it's a point charge with some weird charge there, q1 minus q2 df by dt, located at the origin. So let's just, for future use, call this big Q. Notice that this big Q is time-dependent Q of t. This is the charge density for a point charge at the origin. And the point charge has a charge Q of t. Okay, that was rho. Let's move on to the current density J. Again, we extract it from Maxwell's equations. We evaluate it at a position r at time t, and from Maxwell's equations, we know how to get J. It's related on the one hand to the curl of B, and on the other hand, also to the time derivative of the electric field. And because we know B and E explicitly, we can just go ahead and compute this. And in particular, the magnetic field is 0, so the first term is 0. So we're just looking for the time derivative of the electric field. That's easy peasy. And what do we get? We get Q2 over 4 pi mu naught d squared f by dt squared, all again r hat upon r squared. So we see that the current depends on the second derivative of this function f, and it of course only relies upon the q2 parameter. Okay, all very interesting. Part C, make a gauge transformation phi primed is equal to phi minus d lambda by dt, which is the usual gauge transformation, and a primed goes to a plus the gradient of lambda. And here comes the difficulty in the question. Choose the scalar function lambda such that a primed is equal to 0. Determine phi primed in this case. So what's the logic here? How do we go about tackling this kind of problem? Well, we have a vector potential A here, and what we want to do is add to it the gradient of something which cancels off this term. That's the idea. In particular, we see that the vector potential has an r hat upon r squared term, so the gradient of lambda also must have an r hat over r squared term. So what function lambda, when we take the gradient of it, gives us r hat over r squared? Well, we already discussed it at least twice on this very slide. It's this thing. So the gradient of 1 upon r gives us minus r hat upon r squared, and therefore, just by choosing the constant correctly, if we choose our function lambda to be 1 upon r times something or other, we can arrange for a primed to be equal to 0. And specifically, it's pretty easy to see that what we want is lambda to be q2 f of t over 4 pi epsilon naught r. So when we take the gradient of this, we're going to generate minus r hat upon r squared times q2 f of t over 4 pi epsilon naught. And of course, that will then exactly cancel this original piece. So when I take a plus gradient of lambda, I'm going to get 0, which is exactly what we want. So a primed is equal to the original a, as given upstairs, plus gradient of this lambda. We know that gives equal to 0, which is what we were asked in the question. So with that particular lambda in mind, this actually implies a particular scalar potential phi. So what does that imply? So phi primed is phi minus d by dt of lambda, and lambda does have a time dependence, as we can see from here, and the original phi is given in the question. So plugging that in, we get the following. We get 1 over 4 pi epsilon naught r into q1 minus q2 df by dt. But something rather interesting happened. This q1 minus q2 df by dt is actually our definition of this effective point charge q from part B of the question. That's this object here. And of course, the potential here, the scalar potential, is the same as the potential you would get for a single point charge q located at the origin. So actually this is all making sense. So even though we don't have a scalar potential that looks like the right kind of thing to start with, by performing a gauge transformation, we can see that indeed the scalar potential looks like the scalar potential of a static point charge located at the origin with zero vector potential A primed. So we see that the definition of what ends up in the vector potential and what ends up in the scalar potential is a question of the gauge choice. We can either split it up between A and phi in a particular way, or we can split it up between A primed and phi primed in a different way. And in this particular way, as described, we have zero vector potential and simply a time-dependent scalar potential. It looks like a time-dependent point charge electric potential sitting at the origin. Part D of the question says, determine f of t if the system described is to be a constant point charge q, fixed at the origin, and therefore determine q. So if it's constant, that means the function df by dt must be equal to a constant, and therefore f must be something like at plus b. So let me just summarize that in this bottom right-hand corner of the page here. df by dt is constant because we want the point charge to have no time dependence, so we want df by dt to be constant, and therefore f must be something like at plus b, so that when we take the time derivative we get a constant. And what constant is that? Well, df by dt is obviously then just equal to this parameter a. So the function f is at plus b with constants a and b undetermined, and that tells us that the point charge q is q1 minus q2 df by dt, which is just a q2. So finally we come on to the last question in assignment 4 on dynamics. This is about the relativistic formulation of electromagnetism, and in the end of the question we'll also look at the Lagrangian. So in part A, we're given a relativistic 4-vector equation. It's d mu, j mu is equal to 0. And we're asked to use this to explain the concept of local charge conservation. So the first step is to understand what this has to do with charge conservation at all. So what does this equation mean? First of all, we have the implicit Einstein summation convention, which means we sum of mu over 0, 1, 2, and 3 components. And what that means, considering the definitions that we're provided with in the question, that this d mu means the derivative with respect to the space-time event x mu, and j mu is the 4 current, we can just write this out and see what we get. In particular, we get 1 over c d of c rho divided by dt plus djx by dx plus djy by dy plus djz by dz. And of course that can all be written in a more compact way. You see the c's cancel in this first term as d rho by dt plus the divergence of J. And that's equal to 0, we're told in the question. And of course that is the continuity equation. We're asked in the question to use this to explain the concept of local charge conservation. So here you need to write some explanation for this. The idea is that in the whole universe, the total amount of charge is conserved. Charge is indestructible, so dq by dt is equal to 0 overall. But that's actually not very useful. That's a global concept of charge conservation. What we're interested in is a local concept of charge conservation, in which we consider the amount of charge in a given region of space, a given finite bounded region of space. The amount of charge in that region can, of course, decrease, meaning that the charge density, d rho by dt, is finite. It has a time dependence. For example, the charge can decrease. But the way in which it does that is by there being a charge flux through the walls of that container. And of course, a charge flux is nothing other than the current J. So the change in the charge density is related to a flow in space of the current. We don't allow a bit of charge to instantaneously disappear in one place and miraculously appear somewhere else in space. The charge moves continuously from one place to the other, hence the name continuity equation. So we have a concept of charge conservation. Charge doesn't just disappear, and that has a consequence for the derivatives of rho and j. They're connected in this way. Okay, very good. So that's what that four-vector equation encapsulates. Also, because it's a four-vector equation, we know it's relativistically invariant. It's the same in all reference frames. And that should be the case because charge conservation is a universal concept. Okay, so part B is a bit of a different question. It's about electromagnetic waves, and at the end we have this question about relativity. So we have this equation given for the electromagnetic waves. This is the electric part of the electromagnetic waves, given here as a three-dimensional wave equation, and we're given a solution, a trial solution, which is this electric field given by this expression. And this expression has in it lambda, and we're asked to find the ratio lambda over t such that this trial function is indeed the solution to the wave equation. This is extremely simple. We don't have to solve the wave equation, we just have to plug in this trial wave function and see what happens. So first of all, let's compute the spatial derivative with respect to x. We see, of course, that this electric field trial solution here only depends on x. So when I'm taking the gradient here, or Laplacian as it actually is, I only need to worry about the x component. And in fact, I'll just leap straight to the second derivative because it's not so hard. So d squared e by dx squared is minus 4 pi squared over lambda squared due to the derivatives with respect to x, e naught vector, and then sine, and we get the same thing back again. So it's 2 pi into t upon big T minus x upon lambda. And all of that, of course, is just can be written back in terms of the original electric field as minus 4 pi squared over lambda squared of the original electric field. Very good. What about the second time derivative, which we also need? This is minus, by exactly analogous logic, minus 4 pi squared over big T squared times the original electric field. And we can see that the wave equation is satisfied. If and only if mu naught epsilon naught over t squared is equal to 1 over lambda squared. And since we know that 1 over square root mu naught epsilon naught is the speed of light, we can then write this expression, this condition for the wave equation to be satisfied with this trial function when we have lambda over t is equal to the speed of light c. Okay, so what's the interpretation of these various things? Lambda, perhaps unsurprisingly, is the wavelength. V is equal to lambda over t, which is the speed of light, is the velocity of the wave, or the speed, I guess. Of the wave propagation along the x direction. And of course that implies that capital T is the time period for one oscillation. Good. And of course c is the speed of light. Now the last part of the question is, how fast does the wave propagate in the reference frame of a moving observer? Explain your answers. So we know, of course, that light propagates at the same velocity to all observers. That's the central tenet of special relativity, according to Einstein. So we know that the velocity should be the same in all reference frames. How fast does the wave propagate in the reference frame of a moving observer? It travels with the speed of light, c. Now, the issue is we've got to explain our answers. How do we know that from the mathematics here? We know that because we can actually write the wave equation as a relativistic 4-vector equation. How does that look? Let me just summarize it in this little box here. We can write that d mu, this is a relativistically invariant quantity. That object is actually equal to 1 upon c squared d by dt squared, or minus that thing, plus the Laplacian. And of course that's the thing that features in our wave equation here. So we can write, and we also have one for the magnetic field. And we have to be a little bit careful here because, of course, E and B are, of course, not 4 vectors. So these are not actually 4-vector equations. However, we can, of course, reformulate this in terms of the 4 potential. So in the vacuum, running even more out of space, in the vacuum, I can write this in terms of the 4 potential in this way. And that is a 4-vector equation valid in all reference frames, and that's basically containing this same information about electromagnetic wave propagation in the vacuum. Okay, let's move on to part C. This is a proper 4-vector relativity question. The Lorentz force for a point charge q moving with velocity v in electric and magnetic fields E and B is given by the usual Lorentz force equation for F. So we've broken this question down into some different sub-questions. Let's tackle them one by one. In question 1, in a given reference frame S, the point charge moves with a velocity v is equal to vx along the x direction. Write down the z component of the force. So because the velocity is only along the x direction, the z component of the force from the Lorentz force equation is just q times Ez, electric field along the z direction. But then we've got the cross product v cross b, the z component of which is vx by. In part 2 of the question, consider now the inertial reference frame S primed co-moving with the point charge along the x-axis. So what that means is that v primed is equal to 0, because we're moving along with the particle, so we don't notice that it's moving, because we're moving at the same speed. The relative velocity is 0. Write down the force Fz in the primed reference frame. And I have to do this in terms of components in the primed reference frame. What do I get? Well, that's pretty straightforward. I just get Q times Ez primed. I don't get any magnetic component because the velocity in the primed reference frame is equal to 0. So this is one of the central problems, if you like, of electromagnetism. If I switch the reference frame, it looks like the force has to change, because in the first reference frame I have both electric and magnetic components. In the second reference frame I only have electric components. And of course it's the magic of the whole business that these two are essentially equivalent. To unpack the word essentially, we need to do a bit more work. And we have to do that work in part 3 of the question, so let's just get on with it. It says, find the force Fz primed in S primed, not in terms of the primed components, but in terms of the unprimed components, and then comment. And then what does it look like in the non-relativistic limit? Right, so how are we going to do this? We have to transform the electric and magnetic fields. In particular, what we want is to work out Ez primed in terms of the unprimed stuff. And we do that using the Lorentz transformation, and it even tells us what to do. Here you should use the electromagnetic field tensor, and it's given, together with this Lorentz transformation object, to find F03 primed using the Lorentz transformation. And it's even given. Everything's given. First of all, F03 primed, what's that? Well, it's the 0th row and the 3rd column, and so of course we number 0, 1, 2, 3, so it's 0, and this is the one in question, so clearly we're talking about Ez primed. So let's just write it out. F03 primed is Ez primed over C, actually. And that's what we want to know. And we can relate that to properties of the unprimed system using the Lorentz transformation that's given, namely this one. Just comparing the expressions. 0,3 would give me this thing. And of course, there's an Einstein summation convention implied over sigma, repeated index 1 upper, 1 lower, and lambda, repeated index 1 upper, 1 lower. And then this whole thing is basically just a triple matrix product, and it's a bit tiresome, but we just have to go through it. You need to make sure that you can do this. What you get is the following. This is really a triple matrix product. It's nothing fancy, but you just have to make sure you can go through it and do it for yourself. So we get this result, and that's nice. So we can plug that into our original expression, and we find that Fz primed is equal to Q. We have a factor of gamma. Notice that this C here cancels with this C here when we're actually computing the electric field. So that's, the C is gone. And then it's just Ez plus Vx By. And that's almost exactly what we started with. It's gamma times Fz. So there's something a bit funny about this. It says comment on the result, so now is the time to comment. What we find is that when we turn to a different reference frame, the force, the electric field gets mixed up with the magnetic field in a different reference frame. And we see that directly here, right? So the electric field is now written in terms of the electric and magnetic fields of the unprimed frame. And when you plug it in, the force has this nice structure that looks almost exactly like the force in the unprimed frame. If we look in the non-relativistic limit, as we're invited to do in the question, non-relativistic means that the Vx is much, much less than c, then the gamma goes to 1, and then we have that Fz primed is equal to Fz. And that's what we notice in everyday life. If I have some electromagnetic phenomenon in the lab, and I walk along with my moving charge, I don't notice that there's any difference in the force. So indeed, Fz primed should be equal to Fz. This is the magic of the relativity. And it's this observation that led Einstein to develop the whole theory of special relativity. This is not a coincidence that these two things are equal in different reference frames. But on closer inspection, when we look harder, we see that the forces are not exactly the same because there's this gamma factor. So when the speed's large compared to the speed of light, or an appreciable fraction of the speed of light, there is a difference between these two forces. And the explanation for that, of course, is that when we change reference frame, other things change. For example, our clocks run slow, right? So there's time dilation. And the force is the rate of change of the momentum. And when we're talking about relativity, we're thinking of the 4 momentum, of course. But when we talk about the rate of change of something, that's something involving a time derivative. And then we have to be careful what time we're talking about. We're not talking about proper time, we're talking about coordinate time. And so the punchline of all of this is the physical phenomena themselves look identical in the different reference frames when you take into account also the fact that the force is the rate of change of the momentum, and the rate of change is something that depends on the reference frame as well. So for example, let's say I had a charge that was moving in a magnetic field. Due to the Lorentz force, it feels a force and follows a certain trajectory. If I change reference frame, I would observe the same trajectory. That's the important thing. Even though the force, actually, according to this equation, might look a bit different, the eventual trajectory you observe is the same. Okay, so that's a rather deep and sophisticated answer, but that's the full picture. In terms of this question, all that we need to know really is that the force is equal in different reference frames in the non-relativistic limit. Just to clarify one thing that I mentioned here, when doing the whole thing here depends on doing properly this Lorentz transformation. When I said that it was a matrix product, what I mean is if you compute the entire electromagnetic field tensor as a kind of 4x4 matrix, you can think of that as a matrix product in the following way. The order of these matrices is important. Now, I didn't do all of that because then you have to compute all 16 elements of these matrices, whereas all we're interested in is a very specific component, the 0,3 component, but in principle you can do it as a matrix product like this. Okay, the last part of the last question, the light is at the end of the tunnel. The Lagrangian density for the classical electrodynamics is given by this expression. Use the definitions of the electromagnetic field tensor F, together with how you convert upper and lower indices for such a thing, to derive the covariant form of Maxwell's equations, and they're given. So this is the 4 gradient of the electromagnetic field tensor is equal to the 4 current, and we've got to do that using the Euler-Lagrange equation of motion, which for the classical field theory is given there as well. So this is just working through the machinery of this mathematics. It's a little bit tricky because of the structure of the Euler-Lagrange equation of motion. There's quite a bit going on here. So we've got the Einstein summation convention over lambda here. Oh, sorry, that's a gamma. Over gamma. One is upper, one is lower, and we have to sum over that. And we're left with something that depends on delta. And into that expression, we have to substitute in this expression for the Lagrangian. And to be able to do that and make sense of it, we're going to want to convert this Lagrangian into things involving the 4 potential A, because we're taking derivatives with respect to the full potential A. So when we convert this into potentials, this is all going to drop out. Let's see what happens. Let's start with the easiest piece. Let's look at this piece. We take the derivative, the partial derivative, of the Lagrangian with respect to A delta. Now A features in this Lagrangian here. A is hiding also in the electromagnetic field tensor F through this expression, but that doesn't involve A directly, but derivatives of A. And I'm not taking the derivative with respect to the derivatives of A, just to A itself. Later, I will be taking the derivatives of the Lagrangian with respect to the derivatives of A, and that's in here. But this term is the simple one. So when I take the derivative of the Lagrangian with respect to A delta, I literally just pick up the component in here corresponding to delta, meaning that I just get J delta. Again, that's because I'm taking the derivative with respect to a specific component of the four potential, and in this term of the Lagrangian, I have a sum, because of the Einstein summation convention, over the different components. So I just pick out the particular one that's relevant to taking the derivative with respect to delta. So I just get J delta. Right, so that was easy. What about this term? This is not so easy. First of all, let's notice that here I'm taking the derivative of L with respect to the derivatives of A. So again, by the same logic, this second term is not going to count. So I'm just going to look at this first term here. So I'm taking the derivative of the Lagrangian with respect to derivatives of the four potential. And now you see that I have a product of two of these F's. So we have to use product rule. So I'm going to take the derivative with respect to one of them and leave this one alone. Then I'm going to take the derivative of this one and leave that one alone. So let's just write that out. So by product rule, we get the following two terms. One in which I differentiate this first one, leave this one alone. One in which I differentiate the second one, leave the first one alone. Now, because I'm taking derivatives with respect to the things with the lower indices here, I don't want to see any upper indices floating around. In particular, this is a problem. So let's just write these things in terms of their equivalent versions with the lower indices, and we're given an expression for that here in the question. So we'll just use that directly and write it out. We can write that this F mu nu is F alpha beta with the lower indices contracted with these metric tensors given in the first part of the question, eta alpha mu, eta beta nu, and that goes for this one as well, sitting inside here. And it's exactly the same expression. Notice, however, that these etas don't depend on the potentials, so we can take those out of the derivative. So how do we actually compute these derivatives? Let's be really careful with it. First of all, let's just write out the electromagnetic field tensor in terms of derivatives of the four potential. Note that it's anti-symmetric. Means that if I swap the indices, I just get a minus sign. So what I want to compute is a specific derivative it's the derivative with respect to the derivative with respect to gamma of A delta. So it depends on what mu and nu are as to whether or not this term F mu nu actually contains this particular derivative. In particular, you can see that if mu is equal to gamma and nu is equal to delta, then this F of mu nu contains this term, and when I take the derivative with respect to this object, I get 1. But if mu is equal to delta and nu is equal to gamma, then I pick up -1 from here. And together with this anti-symmetry property, that simply implies the following thing in terms of Kronecker deltas. These Kronecker deltas tell you that this is equal to 1 only if mu is equal to gamma and nu is equal to delta, just exactly the way I said, and it's equal to -1 if nu is equal to gamma and if mu is equal to delta. So this is a bit of a pain, but let's just write it out. The derivative of the Lagrangian now, which is what we really want with respect to this object, is -1 upon 4 mu naught. That was the easy bit. And then we have a bunch of terms coming from precisely this expression. So we just have to be careful with all of the indices, that's all. So that's the first term coming from these objects. And then we have another one with even more indices to worry about. So it's just going through it systematically. And you really should pause the video, I guess, and just try to figure out that this makes sense to you. So again, this first term here is actually both of these things. That's the minus sign in there for this first term, and this one is putting that in for this second term. Okay, now we can actually combine these etas with the f's using this definition, again given in the question, to convert all of this back into electromagnetic field tensors with the upper indices. So we just have to now invert that original process to convert these into f's with upper indices. And we get the following. This is not hard, but it is fiddly, and you have to be extremely careful. And then by using the anti-symmetry property here, that f mu nu is minus f nu mu, and noticing that several of these terms become the same, we obtain the final result, which is -1 upon mu naught of f gamma delta. Excellent. So that's it. In the original Euler-Lagrange equation of motion, we have this object, which we've just computed down here, but notice that it's the derivative d gamma of this thing, and then subtracted from it this object. So let's just plug both of those two terms in and see what we get. So we get d gamma of the thing that we've just worked out, -1 upon mu naught f gamma delta, minus the minus j delta is equal to 0. So if we cancel the minus signs, move the j onto the other side, and multiply by mu naught, then we're going to obtain this final result. And that's exactly what we're looking for. It's Maxwell's equations written in the covariant for vector form, involving the electromagnetic field tensor F and the 4 current J. Now notice that we've swapped all the indices around in here, but those indices are dummy indices and they don't matter. The gamma here is being summed over, so it doesn't matter that that's a mu in this original equation. And then here, we're just looking component by component, nu on the left-hand side, nu on the right-hand side, and likewise here, delta is on the left-hand side, delta is on the right-hand side. So this is indeed Maxwell's equations in 4 vector form. And I think that deserves an exclamation mark. Okay, so that was a bit of hardcore algebra involving these 4-vector equations, but pretty satisfying to get the answer out. And of course, it's wonderful to see that we can write down a simple, single Lagrangian for electrodynamics, and using the usual machinery of classical mechanics, we can obtain Maxwell's equations. So this Lagrangian formulation that takes into account relativity, gauge invariance, and all the rest of it really is the fundamental description. I think this is a really beautiful subject. It's really incredible to see how all of this comes together in this formulation. So that's it. That's the end of assignment 4, and this is about as technical as it gets in this course. So I hope that was useful and good revision for you all.